Hi students, in the last video I gave axiomatic definition of probability. Then we managed to derive some useful results about probability. In the end, we also solved some problems using classical definition of probability. Okay, so let me get started with a problem in this video. Here we go. Say there is a school with n students and you are asked to write a database software to maintain student records. Here the requirement is one should be able to retrieve student records very quickly, almost in constant time using your software. To achieve this fast access, obviously you will be using data structure called hash table. Here, hash table is array-like a data structure where the record is stored at an index which is decided through hashing using some hash function. What hashing is, we feed key of the record to hash function that will spit a number called hash code which may be converted to index of an array if necessary. For example, if the hash code is not falling into the range of indices, then you may have to take modulo of the array size so that result will fall into range of indices. Okay, this is the idea behind hash table. Okay, to do hashing, you need a hash function, right? Let's say for this school project, you have a following hash function in your mind. Okay, here let's say our keys are tuple, full name, date of birth. Okay, this is our key, full name, date of birth. Okay, so if we feed this key to hash function, it will spit a number called d. This d actually day of the year for date of birth. For example, if the student born on 1st January, the d value will be 1. If the student born on 31st December, the d value will be 365. You get the idea, right? So here the d value will be anything from 1 to 365. Okay, that means this hash function only look at the date of birth, then it will give a corresponding day of the year. So that is our hash code, and we are going to take this hash code as it is as index because we are going to work with a array of size 365. So we'll have all these indices from 1 to 365. Fine. Then your hash table may look something like this. Here we have an array of length 366, indices 0, 1, 2, 365, but we are going to use indices from 1 to 365 because our hash code will be from 1 to 365. See, here this record, here is a key, and this student born on 2nd January, so his hash code will be 2, so that's why this record is stored at index 2. If you look at this record, this student born on 31st December, so this key hashes to d value 365, so this record is stored at index 365, like that. Okay, whenever you are trying to access some record, you simply feed key to hash function that will give a index. You directly come to that index and pick your record. Okay, that's how you can retrieve the record very quickly. But one problem with this hashing is collisions. That means two records may hash into same index. For example, two students may have born in same day of the year, right? Okay, this is a problem. One way to deal with this problem is chaining. Instead of storing single record at an index, you maintain linked list of the student records who is hashing into that particular index. Like this, for example. In this case, these two students records, see, both are born on 2nd January. So both hashes into the index 2. So what we do, we put them in a linked list and the head is stored at index 2. Okay, so whenever you want this student record who is born on 2nd January, so when you feed is key to hash function, that will spit a number 2, so directly come to 2, then you search in this linked list. In worst case, you may have to traverse through old list. So we don't want this list to too big, right? So that's why here we like to avoid clusters, so that we don't want to see one list is at one index list is too big and at one index list is too small, not like that. So we want our hash functions to be good enough to distribute these keys over indices uniformly. Okay, let's say our hash function does that. Our hash function uniformly distribute keys over these indices 1 to 365. Still, we like to have less number of collisions because having less number of collisions reduce average retrieval time for record. So, to achieve that fast access, almost constant time, in this setup, we have a 365 slot. We can't use too many students, right? If you use too many students, what happens? Average length of the list will be more. In that case, you may have to spend some time to get the record from each list. Okay. Okay, but having less than 365 number doesn't mean that we can't have any collision. Do our hash function uniformly distribute keys over indices. Okay, but one thing is clear that less number of students means less chance of collision. So we will have less number of collisions. More number of students means more chances of collision. So more number of collisions. But what exactly is trade-off between number of students and the probability of having collisions? So we want to address this question. Okay. So for example, if there are 23 students in the school, what do you think about the chances of having collisions? You may feel that there are 365 slots and our hash function uniformly distribute keys over the indices, so there would be very less chance of having collision. You may feel that. What do you think chances of having collision if there are 60 students? Still you may think that chances are not much, it may be very less, okay, because 365 versus 60, right? We are going to address this problem. The solution is going to be surprising. Okay, so this question will be answered through a famous problem called birthday problem, or you can say birthday paradox. Okay, if n people are present in a room, what is the probability that at least two of them celebrate birthday on the same day of the year? If n people are in a room, what is the probability that at least two of them having same birthday? Okay. Okay. First, let us assume that nobody born on the leap year. Okay. There are two cases here. Here, case 1, n bigger than 365. If there are more than 365 people in a room, then it's going to be a sure thing, right? By pigeonhole principle, you can always find at least two people having same birthday. In that case, the probability going to be 1. So the probability of at least two people having same birthday will be 1 in this case, okay? Because of pigeonhole principle. Case 2, n less than or equal to 365. Let's assume that a person could be born on any day of the year with same probability. Actually, it can't be true because there are some seasonal effects. It means in some seasons more marriages takes place. After 9 months of that season, more babies are born. That's why we can't simply assume that a person could be born on any day of the year with same probability. But with this assumption, our outcome is going to be equally likely, so that we will be able to apply classical definition of probability to compute the probability. So the problem become easy. But with this assumption, the answer we get will be pretty close to the answer you get in reality. Reality means if you go to some 100 classes and get the data, and if you do this experiment, you will realize that the answer is pretty close to the answer we get here. Okay, it won't make much difference if you make this assumption. The only thing is the problem become easy and the answer will be very reasonable to the reality. Okay, don't worry. Now outcomes. We are going to observe birthdays of n people, right? So this is how I am going to describe outcome. Okay, like this: b1, b2, so on, bn. Let's say there are n people, person 1, person 2, so on, person n. Here the b1 represent birthday of the person 1, b2 represent birthday of the person 2, so on, bn represent birthday of the person n. Okay, each bi can be anything from 1 to 365. Okay, now if you look at carefully, these look like n permutations of n permutations of 365 objects with repetition, because your birthdays can be repeated, right? So that's why these are like n permutations of 365 objects with repetition, and we know how to count permutations with repetition, right? That's why the number of elements in omega are going to be 365 to the power of n. Okay, fine. Now let E denote the event that at least two people in the room having same birthday. Okay, so what we do, we first compute the probability of E complement, because computing probability of E complement will be easier than computing probability of E directly. Then we use the relation, the probability of E going to be 1 minus probability of E complement. Okay, probability of E equal to 1 minus probability of E complement, right? So where E complement denote the event that no two people in the room having same birthday. E denote the event that at least two people in the room having same birthday. Then E complement should be opposite, right? That means no two people in the room having same birthday. Okay, let's try to compute the probability of E complement first. Then we use this relation to compute probability of E. Okay, first of all, what is E complement? See, E complement consisting of all outcomes in which no two people having same birthday. That means all having different birthdays. They look like this: B1, B2, so on, Bn, where each Bi is going to be anything from 1 to 365. One more thing is, all birthdays are different. That means Bi not equal to Bj for I not equal j. Now these candidates look like n permutations of 365 objects without repetition. Here all should be different, all bodies should be different, so without repetition. We also know how to count permutations without repetition. That's why number of elements in E complement going to be 365 Pn. Okay, this is the count for E complement. Okay, now the probability of E complement going to be number of elements in E complement by number of elements in omega, because we assume that outcomes are equally likely, so we can apply classical definition. So according to that, the probability of E complement will be 365 Pn by 365 to the power of n. Now the probability of E going to be 1 minus probability of E complement, which is 365 Pn by 365 to the power of n. Therefore, probability of at least 2 people in a room of n people having same body is going to be 1 minus 365 Pn by 365 to the power of n. This is the probability. Okay. Now, I've written a small Python code to compute this probability. Okay. So we'll check for various values of n. Okay. Let me clear this. Next. Feel free to understand this code. It's very easy. Let me run it and check these probabilities for various values of n. Okay. First, let me check for n equal 23. Yeah. When n equal 23, the p-value is 0.5073. That means when there are 23 people in a room, the probability of at least 2 people having same birthday is 0.5073. That means there is a 50% chance that at least 2 people will have a same birthday. If you go back to our school project problem, then if there are 23 student records, then the probability of having collision will be 0.5073. This must be surprising, right? Let's check for other values. For n equal to 30, the p-value is 0.7063. For n equal to 40, the p-value is 0.8912. For n equal to 50, p-value is 0.9704. When n equal to 60, p-value is 0.9941. That means if there are 60 people in a room, then probability of at least 2 people having same birthday is 0.9941, almost certain. In our school project problem, if there are 60 student records, then probability of having collision will be 0.9941. So almost all the time we will have a collision. Okay. So these results must be surprising, but these are true results. You can actually verify them by doing some experimentation. What you can do is you go to some 100 classes of size 60, then you get the data and verify. You will see that at least 99 classes will have a 2 or more people having same birthday. Okay, fine. But these results are very counterintuitive. That's why this problem is called paradox, birthday paradox. Okay, fine. Here is a table for various values of n and corresponding the probability values. Okay, and when n equal to 70, the p value is 0.9992. Okay, so that's the thing. Now let us formalize this birthday problem in terms of hashing and collisions. Okay, the problem let the range of hash function is 1 2 3 so on k. This hash function take the key and produce a number from 1 to k, which we will use as the index of an array. Okay, and the number of records that we insert is n. Okay, and the hash function produces a perfectly uniform distribution of keys used in insertion. See, in birthday problem also, we assume that a person could be born on any day of the year. That's what we mean by these birthdays are uniformly distributed over the 365 days. Okay. Then the probability of at least one collision occur is 1 minus kpn by k power n. Okay. So this is the probability of having collision when you have a n records and using a hash table of size k. Okay. This is a computer science problem. Okay. Next. Problem 4. Suppose the probability of A equal to 3 by 4 and probability of B equal to 1 by 3, then show that the probability of A intersection B is lies between 1 by 12 and 1 by 3. Okay. So first of all, we know that probability of any event lies between 0 and 1, right? So in particular, probability of A union B should be between 0 and 1. So we know that 0 less than or equal to probability of A union B less than or equal to 1, right? And probability of A union B in terms of probability of A, probability of B, and probability of A intersection B is this. Probability of A plus probability of B minus probability of A intersection B, which is less than or equal to 1. Now we know probability of A and probability of B values. So 0 less than or equal to probability of A 3 by 4, probability of B 1 by 3 minus probability of A intersection B less than or equal to 1. That implies 0 less than or equal to, it will be 9 plus 4, which is 13 by 12 minus probability of A intersection B less than or equal to 1. So if we multiply minus each side, minus 1 less than or equal to probability of A intersection B minus 13 by 12 less than or equal to 0. Now if we add 13 by 12 each side, 13 by 12 minus 1 less than or equal to probability of A intersection B less than or equal to 13 by 12. Okay. Now this is going to be 1 by 12 less than or equal to probability of A intersection B less than or equal to 13 by 12. This is one relation we got. Now also here it's pretty clear that A intersection B is always subset of B and the empty subset always subset of any set, in particular A intersection B. So we have this relation. If you apply probability, then the probability of pi less than or equal to probability of A intersection B less than or equal to probability of B, because of monotone property of probability. Monotone property. So the probability of empty set is 0 less than or equal to probability of A intersection B, and the probability of B is 1 by 3. So this is 2. From 1 and 2, we can conclude that if you look at 1 and 2, then you can say that the probability of A intersection B lies between 1 by 12 and 1 by 3. Okay. This is the, we're done. Okay. Monotone sequence of events. A sequence of events En is said to be increasing if En is contained in En plus 1 for all n. In this case, limit En defined to be union n equal to 1 to infinity En. This is what we mean by limit En when we have an increasing sequence of events. Similarly, we define decreasing sequence of events. A sequence of events En is said to be decreasing if En contains En plus 1 for all n. In this case, limit En defined to be intersection n equal to 1 to infinity En. This is what we mean by limit En in the decreasing case. Okay. Now, a sequence of event is said to be monotone sequence if it is either increasing or decreasing. Okay, either this type or this type, such a sequence of events is called monotone sequence of events. Okay, Now let me give two examples, one of each type. Okay. The first one, here En equal to closed interval 1 by n, 3 minus 1 by n. Okay. If you look at, let me locate these intervals. Here let us say 0, 1, 2, 3, 4 and so on. Okay. E1. What is E1? When n equal to 1, you will have 1 by 1, comma 3 minus 1 by 1 means you will get 1 comma 2. Interval 1 comma 2. So what is E1 here? This is E1. Okay. This is E1. Next E2. E2 will be 1 by 2 to 3 minus 1 by 2. So it will be from here onwards. 3 minus 1 by 2 means 2.5, like here. Okay. Next E3 will be 1 by 3 to 3 minus 1 by 3. So it will be from here on, from here to something like here. Okay. As you see, one is contained in other. E1 is contained in E2, E2 is contained in E3 and so on. Okay. So we have this. This is E1 is contained in E2, it is contained in E3 and so on. Okay. That's why this sequence is increasing sequence of events. Okay. So in this case, if you look at a union, see, if you take the union of all these En, you will get open interval 0 to 3, because we will not cover 0 because no En contains 0, right? It's going to close as n getting bigger and bigger, the left hand point approaching 0 but never contains 0. Okay. Similarly, as n getting bigger and bigger, the right hand point approaching 3 but never contain 3. That's why we will never include 0 and 3 in our union. So, but it can include everything else. Okay. So this union going to be open interval 0 to 3. Okay. So in this case, this limit En means interval 0 to 3 in this particular case. Next, example 2. Here En equal to 2 plus 1 by n. So let's say this is 2, 3, 4, 5 and so on. Okay. Now, so what is E1? E1 going to be 2 to 2 plus 1 by 1. That means 2 to 3. So this is going to be E1. E2 going to be interval, closed interval 2 to 2 plus 1 by 2. That means from here to here. That is E2. Then E3 going to be closed interval 2 to 2 plus 1 by 3. That means here to something like here. Okay. As you see, E1 contains E2 and E2 contains E3 and so on. Okay. So in this case, we have a decreasing sequence of events. If you look at intersection of all these events, the limit En going to be intersection of all these events, it will be singleton 2, because as you see, this 2 is a left hand point which is a part of every n, but nothing else will be in the intersection of all en's, because as n getting bigger and bigger, 2 plus 1 by n will be approaching 2, no matter what you point here. Okay. So whatever you take, then there is a n which come left side of that point. So that's why, so intersection will not contain anything else. So it will contain only singleton 2. So in this case, limit En is going to be singleton 2. Okay. Fine. Let me clear this. Next, theorem 9, continuity of probability set function. Okay, first of all, you know what is the meaning of a function of real variable is continuous at a point A, right? If let us say f of x is a function of single variable, if it is continuous at A, there is a sequence characterization. That means we say if any sequence an converges to A, then f of an converges to f of A, right? That means limit an equal to A, then we have limit n tends to infinity f of an equal to f of A. Okay, this is a sequence characterization for continuity. Whenever an approaching A, then f of an approaching f of A, whenever f is continuous at A. So here f of A, what is A? Limit n tends to infinity an, right? This is the right hand side. What is the left hand side? Limit n tends to infinity f of an. See, we are interchanging the limit. When f is continuous at A, we can interchange this limit. Here also, it looks same. We interchanging the limit. Probability of limit is limit of the probability. Okay, that's why we call continuity of probability set function. Fine? Okay. Now let's prove this. Okay, let's prove this. If sequence of events En is monotone sequence, then probability of limit En is limit of probability of En. Please understand here, the left hand side limit is limit of monotone sequence of events, which either mean union of Ens or intersection of Ens according to whether it is increasing sequence of events or decreasing sequence of events. But the right hand side limit is, here probabilities are real numbers, right? So the right hand side limit is limit of sequence of real numbers. Okay, so please understand the limit in left hand side and right hand side. Okay, now let's prove it. Proof. First, case 1. See here, En is monotone sequence. So monotone sequence means either increasing sequence of events or decreasing sequence of events. So first let us do the case En is increasing sequence of events. That means E1 is contained in E2, E2 is contained in E3, and E3 is contained in E4, and so on. En is contained in En plus 1 in general. Okay, so this is the increasing sequence of events. If I draw a picture, it looks something like this. E1, E2, E1 is part of E2, E1 is contained in E2, then E2 is contained in E3, and so on. Okay. Now let us define new sequence of events out of this sequence. Okay, like this. First, F1 is same as E1, so this is F1. Next, F2 going to be, here Fn is defined as En intersection with union I equal to 1 to n minus 1 Ei whole complement. Simple. We just take outcomes of En which are not covered from previous Eis from 1 to n minus 1. Those are collected in Fn. Simply, we are constructing this sequence F1, F2 in a way that we take F1 same as E1, we take F2 all things on E2 which are not covered in F1. In F3, we take all things in E3 which are not covered in F1 and F2 and so on. Okay, so that we will not have any overlapping, so we will end up with mutually exclusive events. That's the idea. Okay, then So F2 going to be this. Okay, then F3 going to be this, like this. Okay, so F1 is same as E1. F2 going to be, for example, F2 going to be E2 intersection union I equal to 1 to n minus 1 means simply it's going to be E1 complement, which is simply E2 minus E1. Okay, simply all outcomes in E2 which are not in E1. Okay, because E1 outcomes already covered by F1, so we don't have to take again. So we want to have a mutually exclusiveness. That's why we are constructing this way. Okay. So this is an idea. Fine. Here we are not missing any outcome. We are covering all outcomes. That the only thing is we don't repeat. Okay. If something is covered by some previous FI, we will not include in future FI. That's the idea. Okay. So that's why the union of FIs for I equal to 1 to infinity will be same as union of I equal to 1 to infinity EI. Everything will cover. Only thing is we will not repeat. And also union I equal to 1 to an Fi will be same as union I equal to 1 to an Ei. Whatever covered by up to En will be covered by all Fi's from 1 to n. Okay. And union I equal to 1 to an Ei will be same as En, because increasing sequence of events, right? E1 is contained in E2, so E1 union E2 will be E2. E2 is contained in E3. So E1 union E2 union E3 will be E3, like that. So union I equal to 1 to and EI will be same as En. Fine. Next. So here we can see that F1, F2, F3, so on, this sequence of events going to be mutually exclusive. We made sure that the way we constructed F5s, we wanted them to be mutually exclusive events. Okay, we made sure that. That's why F1, F2, so on, these are mutually exclusive events. Now here the probability of limit En. See, limit En is nothing but union of n equal to 1 to infinity En in the increasing case, right? Okay, that's why the probability of limit En we are writing probability of union of En, but this union is same as union n equal to 1 to infinity Fi is, right? Because of this. Okay. So in the next step, let me clear this. Next step, so I'm going to replace union n equal to 1 to infinity En with a union n equal to 1 to infinity Fn. Okay, the good thing about this union is now these Fi's are mutually exclusive. So we can apply axiom 3. Okay, so this probability going to be summation n equal to 1 to infinity probability of Fn because of axiom 3. Axiom 3 can be applied when you have a mutually exclusive events. Okay. Fine. Now, but this is the infinite series, right? N equal to 1 to infinity, infinite series of real numbers. Okay. So, infinite sum means the limit of the partial sums. Okay. That's why I'm taking limit n tends to infinity summation I equal to 1 to n probability of Fi. Okay. This is a sequence of partial sum. I think you know the meaning of summation n equal to 1 to infinity an. If this series converges, then this will be defined as limit n tends to infinity Sn, where Sn is sequence of partial sum from I equal to 1 to an I hope you know this. Here Sn is nothing but this summation I equal to 1 to n probability of Fi. Okay. Now here F1, F2, so on, Fn are mutually exclusive. So by additivity, finite additivity, this probability can be written as probability of union I equal to 1 to n Fi. Because of finite additivity, this probability is same as this. Okay. Here this union I equal to 1 to n Fi is same as union I equal to 1 to n Ei. Whatever outcomes that are covered in E1, E2, En will be covered in F1, F2, so on, Fn also. Okay. So that's why union I equal to 1 to n Fi same as union I equal to 1 to n Ei, but this is same as En because of increasing sequence, right? EIs are increasing. E1 is contained in E2, E2 is contained in E3 and so on. Okay. Now, fine. So that's why this union is nothing but union of EIs from I equal to 1 to n, which is nothing but En. That's why this union is replaced with simply En. Okay, so therefore we got probability of limit En is limit of probability of En. Okay, so this is a proof in increasing case. Fine. Okay, next let us do case 2. Case 2, we have to deal with decreasing case. So we don't have to do everything from scratch in a decreasing case. We can make use of this result by applying something called De Morgan laws. Okay, so let's see. Next, case 2. If you take En, which is a decreasing sequence of events, that means E1 contains E2, E2 contains E3, E3 contains E4 and so on. In general, En contains En plus 1, so on. Okay. In this case also, we want to show that probability of limit En is same as limit of probability of En. But in this case, limit En means intersection of n equal to 1 to infinity, right? Anyway, fine. So, we wanted to apply the previous case. So for that, let us look at their complement. Here we have a En, which is a decreasing sequence of events. If you look at their complement, they will become increasing sequence of events. Okay, look at En complement. Okay, then it's going to be increasing because En contains En plus 1 means En complement contained in En plus 1 complement. Okay, just feel free to verify. It's a easy fact. Okay, now here you can apply case 1. So if you apply case 1 to this En complement sequence, as this is increasing sequence, now the probability of limit En complement going to be limit of probability of En complement. But what is the meaning of limit En complement? Here En complement is increasing sequence of events, right? So it's going to be union of En complement. So next step, I'm going to replace this limit En complement with union n equal to 1 to infinity En complement. And the right hand side, this probability of En complement, I'm writing 1 minus probability of En. Now using De Morgan laws, we can write this union n equal to 1 to infinity En complement. We can write complement of intersection n equal to 1 to infinity En due to De Morgan laws. Now, if you apply limit of constant sequence 1 minus limit of this sequence, simply going to be 1 minus limit of this. Now, again, probability of complement of this event going to be 1 minus probability of this event. That's why 1 minus probability of intersection n equal to 1 to infinity En. Okay. Now this 1 cancel, minus cancel. So what we have the probability of intersection n equal to 1 to infinity En, which is limit n tends to infinity probability of En. But here En is decreasing sequence of events, right? So in this case, intersection n equal to 1 to infinity En nothing but limit En. That's why in this case also we have the probability of limit En is same as limit of probability of En. Okay, so this is the continuity of probability set function. Fine. Next, subadditivity of probability. Here is a statement, theorem 10. For any two events in event space, probability of E1 union E2 always less than or equal to probability of E1 plus probability of E2. This equality happens only when E1 E2 are mutually exclusive. That follows from additivity of probability. Okay, finite additivity. Okay, in general we have this inequality. Okay, the proof is easy. From addition theorem of probability, we know that probability of E1 union E2 exactly equal to probability of E1 plus probability of E2 minus probability of E1 intersection E2. And we also know that from axiom 1, probability of any event always non-negative. So this is going to be non-negative. So if you want to get rid of this term, so you must keep the inequality like this. Probability of E1 union E2 less than or equal to probability of E1 plus probability of E2 after getting rid of this term. Okay, since probability of E1 intersection E2 non-negative by axiom 1. So this is the subadditivity property for two events. Okay. Now let's generalize for n events. Theorem 11, for E1, E2, so on n events in event space, then probability of union I equal to 1 to n ei always less than or equal to summation I equal to 1 to n probability of ei. Here also equality happen by finite additivity only when E1, E2, so on En are mutually exclusive. In general, we have this inequality like this. Okay. The proof is by induction. You can use n equal to 2 as a base case. So I'll let you try. The proof by induction, use n equal to as a base case. You can prove. Okay. This is the subadditivity for n events. Okay. Okay. Theorem 12. Countable subadditivity. Here is a statement. For any countable collection of events E1, E2, so on, En in event space, the probability of their union going to be less than or equal to sum of their probabilities. That is, the probability of union I equal to 1 to infinity Ei less than or equal to summation I equal to 1 to infinity probability of Ei. This is the countable subadditivity statement. Here, this collection is any countable collection of events in event space. If they are mutually exclusive, we know that from axiom 3, we have equality, right? But in general, if you don't know that, what you can say is from countable subadditivity, this probability of the left hand side less than or equal to right hand side. Okay. Now, let's prove this. Okay. What we are going to do now, we are going to define new countable collection of events f1, f2, f3, so on in terms of these AIs. In a way, the new collection going to be mutually exclusive, so that you will be able to apply axiom 3, and they're still going to cover exactly what this E1, E2, so on En covers. Okay, that is an idea. So this is how we are going to define new collection of events. We define F1 exactly same as E1, but Fn going to be equal to En intersection union I equal to 1 to n minus 1 Ei whole complement for n equal to 2, 3, 4, so on. What it means here, Fn consisting of outcomes in En which are not covered in E1, E2, so on up to n minus 1. That is the meaning. Okay. Fn contains outcomes in En which are not covered in E1, E2 up to En minus 1. Okay, that is the meaning of this expression. That, for example, F1 is same as E1, but F2 going to consisting of outcomes in E2 which are not in E1. F3 going to consisting of outcomes in E3 which are not covered in E1 or E2. You get the idea. Okay. So, in this way, we end up with a mutually exclusive collection of events, and they still exactly cover what this E1, E2, so on En covers. Okay, fine. Also, one thing we can see, this Fn actually part of En. Fn is what? En intersection with something. So, Fn always subset of En. So, Fn is always subset of En. That implies probability of Fn less than or equal to probability of En for all n because of monotone property. Okay. And now this new countable collection of events is going to be mutually exclusive, right? Okay. We also realize that the way we constructed, we made sure that our new collection is going to be mutually exclusive because we made sure that there is no overlapping while we constructed. Because when we are constructing, if some outcome already included in some previous F5, we will never include in future F5s. That's how we constructed. So that will guarantee that our new collection is going to be mutually exclusive events in event space. Okay, and they're still going to cover what exactly this EIs covers. So if you take the union of EIs from I equal to 1 to infinity, that would be exactly same as union of F5s from I equal to 1 to infinity. Okay, so if you take the probability both sides, the probability of the union I equal to 1 to infinity is same as the probability of union I equal to 1 to infinity Fi. The good thing about right hand side is you can apply axiom 3 because you know F1, F2, so on, Fn, this countable collection are mutually exclusive. Okay, so you can apply axiom 3. So the right hand side equal to summation I equal to 1 to infinity probability of Fi because of axiom 3. In the above slide, we realize that each Fi is a part of A, right? Okay, so for all I, so by applying monotone property, the probability of Fi is going to be less than or equal to probability of Ei for all I due to monotone property. So this summation will be less than or equal to this summation because each term here, the probability of Fi less than or equal to probability of Ei. So this whole sum will be less than or equal to this whole sum because we know that probability of Fi less than or equal to probability of Ei for all I because of monotone property. Okay. So therefore, we have this countable subadditivity. The probability of union I equal to 1 to infinity Ei less than or equal to summation I equal to 1 to infinity probability of Ei. This is the countable subadditivity. This inequality also called Boole's inequality. Okay. Now we are going to talk about an interesting paradox. Here we go. Say we have a large box with infinite capacity and infinite collection of balls with a label 1, 2, 3 and so on. Okay. Let us consider the experiment performed as follows. At a 1 by 2 power I minute to 12 pm, balls with a label 10 times I minus 1 plus 1 to 10 times I are added to the box and ball with a label 10I is removed for I equal to 1, 2, 3, so on. We assume that it takes no time to add or remove ball from the box. Okay. Now let me explain here. At a 1 by 2 minute to 12 pm, balls with a label 1, 2, 3, so on, 9, 10 are added to the box and ball with the label 10 is removed. At a 1 by 4 minute to 12 pm, balls with the label 11, 12, 13, so on, 19, 20 are added to the box and 20 is removed. At a 1 by 8 minute to 12 pm, balls with a label 21, 22, so on, 29, 30 are added to the box and ball with a label 30 is removed and so on. Okay, you get the idea. Now, question of interest is how many balls in the box at 12 pm? Finite, infinite or empty? This is easy. Answer is infinitely many balls will be there at 12 pm. Okay. The reason is the only balls we ever removing from the box are balls with a label that are multiple of 10, like 10, 20, so on. Remaining all balls will be there in the box at 12 pm. So answer is infinite. There will be infinitely many balls in the box at 12 pm. Okay, let's make a small change in the experiment. Let me clear it. Now let's change the experiment slightly. At a 1 by 2 power I minus 2 12 pm, balls with a label 10 times I minus 1 plus 1 to 10 times I are added to the box, and ball with a label I is removed for I equal to 1 to so on. At 1 by 2 minute to 12 pm, balls with the label 1, 2, 3, so on, 9, 10 are added to the box, and ball with the label 1 is removed. At a 1 by 4 minute to 12 pm, balls with the label 11, 12, so on, 19, 20 are added to the box, and ball with the label 2 is removed. At a 1 by 8 minute to 12 pm, balls with the label 21, 22, so on, 29, 30 are added, and ball with the label 3 is removed, and so on. Now again, same question. How many balls in the box at 12 pm? This time answer will be 0. That means the box will be empty. That means box will be empty at 12 pm. Okay, I don't know how many of you can see this. Here, in this process, every ball eventually get removed. Okay, at 12 pm there will not be any ball. Okay, you have to think logically. Don't think like you are doing experimentation, because you can't do experiment because there are infinitely many balls involved here. Okay, think logically. So you name the ball. Say you name the ball K. This ball get removed at a time 1 by 2 power k minute to 12 pm. 12 pm. Okay. You name the ball with the label K that gets removed at 1 by 2 power k minute to 12 pm. So every ball gets removed at some point of time. So logically there will be no ball at 12 pm. Okay. So this time box will be empty at 12 pm. Fine. Okay. So the manner in which we remove the balls actually make the difference, right? Okay. So now again, let's make another change to this experiment. Now let's change the experiment again. At 1 by 2 power I minus 2 12 pm, balls with the labels 10 times I minus 1 plus 1 2 10 times y are added to the box, and the random ball is removed from the box for I equal to 1, 2, so on. So this time what we are doing is, at a 1 by 2 minute to 12 pm, balls with the label 1, 2, so on, 10 are added. A random ball is removed from the box. Okay. Again, at a 1 by 4 minute to 12 pm, balls with the label 11, 12, so on, 20 are added. Now the box will have 19 balls. You just pick one ball at random. Okay. That's what we are doing. At 1 by 8 minute to 12 pm, again we add 10 more balls with the labels 21, 22, so on, 30. Again we pick a one ball at random, and so on. Okay. This time I'm not going to ask the same question because it won't make sense. Okay, now it is a random experiment. Okay. At least two possible answers will be there, because the cases we consider above may come here, because though you are picking at a random, you may pick at the first removal you may get a 10, second removal you may get a 20, third removal you may get a 30, and so on. In that case, the box will have infinitely many balls at 12 pm. Or it may happen that though you are picking at a random, at first removal you may remove 1, at second removal you may remove 2, at third removal you may remove 3, and so on. If this happens, then box will be empty at 12 p.m. So there are more than one possible answer. So that question will not make sense. If I ask you how many balls will be there in the box, then answer maybe empty or infinite. I don't know. Okay, so it may be anything. But rather, we can ask you, as it is a random experiment, the following question makes sense. With what probability box will be empty at 12 p.m.? Okay. Now we are going to show that with probability 1, the box will be empty at 12 p.m. Okay. That means almost all the time box will be empty at 12 p.m. Okay. So it's very rare that box being non-empty at 12 p.m. Fine. Okay, now we are going to show that this is actually very counterintuitive. Okay, people can't see this. So with probability 1, box will be empty. Okay, so fine. Let's do this. Okay. First, let us focus on ball with a label 1. Okay. Let En denote the event that ball 1 in the box after first end removals. It means En denote the event that not touching ball 1 in the first end removals. Okay. Let's compute the probability of En. Here we remove balls at random, so we can assume outcomes are equally likely. So we will be using classical definition of probability, compute probability of En. Okay, so probability of En going to be number of outcomes that are favorable to En by total number of outcomes. Okay, here we are doing end removals, right? Okay, let us see the total number of ways this end removals can be done. In first removal, there will be 10 balls. We can remove any one of the 10 ball, right? So 10 ways can be done first removal. And in second removal, 9 plus newly added 10. So there will be 19 balls. We can remove any one of them. In third removal, there will be 28 balls. We can remove any one of them, right? So 28 ways. In so on, in nth removal, there will be 9n plus 1 balls. We can remove any one of them. So it can be done in 9n plus 1 ways. So the number of ways this n removals can be done is 10 into 19 into 28 into so on 9n plus 1. Now, how many of them actually favorable to not touching ball 1? Okay, now in the first removal, there are 10 balls in which one ball with a label 1, right? And we don't want to touch it, so we can remove any one of the 9 remaining balls. Okay. In second removal, there will be 19 balls in which one ball with a label 1 and we don't want to touch it, so we can remove any one of the 18 balls and so on. At the nth removal, we have 9n plus 1 balls in which one ball with a label 1 and we don't want to touch it, so we can remove any one of the 9n balls. So the number of ways these n removals can be done without touching ball 1 is 9 into 18 into 27 into so on 9n. Okay, so therefore the probability of En going to be this. This expression can be written using product notation like this. Product I equal to 1 to n 9i by 9i plus 1. As you can see, 9 by 10, 18 by 19, 27 by 28, all of them in the form 9i by 9i plus 1 for I equal to 1 to n. Okay, so okay, fine. This is the probability of En. Now let F1 denote the event that ball 1 in the box at 12 p.m. Ball 1 in the box at 12 p.m. means ball 1 still in the box after all removals. That means we are never touching at any removal. That means E1 must have happened, E2 must have happened, E3 must have happened, so on. If all En happened, then only you will see ball 1 in the box at 12 p.m. That's why this F1 can be expressed in terms of ENs like this. F1 is intersection of n equal to 1 to infinity En. Okay, this F1 can be expressed in terms of En precisely like this. Okay, now, and here En plus 1 is contained in En. That means whenever En plus 1 happen, then En happens. Because if you see ball 1 at n plus 1th removal, you must have seen ball 1 in nth removal also. That's why. Okay. That means we have a decreasing sequence of events. Okay. This sequence En going to be decreasing sequence of events. So now this F1 actually we can write in the limit notation, limit n tends to infinity En. Okay. So here En is decreasing sequence of events, right? So limit En exactly equal to this intersection of En from n equal to 1 to infinity. Fine. So therefore F1 we can write limit of En. Okay. Now if you want probability of F1, the probability of F1 going to be probability of limit En. Now if you apply continuity of the probability, this is going to be equal to limit of probability of En. So this is equal to probability of limit En going to be limit of probability of En because of continuity of probability. Okay. Now the probability of En we already got. So this is going to be limit n tends to infinity, the probability of En I am replacing with this expression product I equal to 1 to n 9i by 9i plus 1. So let me write this one as a reciprocal of something. So this one I am writing 1 by product I equal to 1 to n 9i plus 1 by 9i. I hope you can see that. And limit of the reciprocal same as reciprocal of the limit. So I can write next step 1 by limit product I equal to 1 to n 1 plus 1 by 9i. Same thing I am writing 1 plus 9i. You can see this. Now I am going to realize that this limit is going to be infinity. Then I can say that probability of F1 0. Okay, because the product I equal to 1 to n 1 plus 1 by 9i. Okay, which means actually what? 1 plus 9 into 1 plus 1 by 18 into 1 plus 1 by 27 into and so on 1 plus 1 by 9n, right? If you multiply, you will see at least some terms like 1 by 9, 1 by 18 and so on 1 by 9. At least these terms you will get. There will be more. That's why the left hand side will be greater than or equal to this. If you take 1 by 9 common, 1 plus 1 by 2 plus 1 by 3 plus so on 1 by n. Okay, but now you know that this is the sequence of partial sum of harmonic series. Harmonic series 1 by n equal to 1 to infinity. This diverges to infinity, right? So this limit go to infinity. Okay, therefore if this limit go to infinity, obviously this limit also go to infinity, right? Okay, that's why here the denominator going to be infinity, so answer going to be 0. So therefore the probability of F1 going to be 0. Fine. Okay, next let Fk denote the event that ball with a label k in the box at 12 p.m. With a similar reasoning, one can show that probability of Fk 0 for all k equal to 1, 2, 3. Just like the way we did for ball 1. Okay. Let E be the event that box will be empty at 12 p.m. Then E complement will be the event that box will be non-empty at 12 p.m. Non-empty at 12 p.m. means at 12 p.m. the box should have at least one ball with a label 1 or label 2 or label 3 or so on, right? That means at least one of the event F1 or F2 or F3 or so on, some Fk should happen, right? That's why this E complement can be expressed in terms of these Fk's like this. E complement will be precisely union k equal to 1 to infinity Fk. That means this is precisely mean by box non-empty at 12 p.m. because this means at least one of the Fk must have happened. That means at least one ball with some label K is there in the box. Okay. So now the probability of E complement going to be same as the probability of union K equal to 1 to infinity Fk. Now here we can apply Boole's inequality. So this will be less than or equal to summation K equal to 1 to infinity probability of Fk because of Boole's inequality. But and we know that probability of Fk is 0 for all K. So this right hand side all sum will be 0. That means the probability of E complement must be less than or equal to 0. And we know that from axiom 1, the probability must be non-negative for any event. So therefore, the probability of E complement must be 0. So with probability 0, box will be non-empty at 12 p.m. Now, probability of E going to be 1 minus probability of E complement, which is 1 minus 0. So the probability of E going to be 1. So hence the probability of box will be empty at 12 p.m. is 1. With probability 1, the box will be empty at 12 p.m. Fine? Okay. You must be wondering that we have already seen one possibility of box being non-empty when we remove balls like a 10, 20, 30, 40, so on. What do you mean by with probability 1 box will be empty at 12 p.m.? Okay. Thing is, probability of some event 1 doesn't mean that it is a sure event. In the same way, probability of some event 0 doesn't mean that it is an impossible event. In this case, with probability 1 box will be empty means almost all the time box will be empty. Box being non-empty at 12 p.m. hardly happens. Okay, that's what it means. Maybe I'll talk more about these things in future. Okay, so let me stop. Thank you.